everybody. So it's my pleasure to introduce Professor Felix Dean. As you know, he's one of the most important heterodox economists in the world. Probably you know his book, Debunking Economics, which is now in its second edition, right?
That's right, yeah.
Well, he's well known around the world because he's one of the few economists who correctly predicted the financial crisis, the last financial crisis. And, well, we are very happy that he's here with us. And I want to share another very good news with you. This team is going to work with FLACSO next year. And our goal will be to develop a macroeconomic model for Ecuador. And I know some of you will be interested in participating in this project, so we'll keep you updated. And well, that's it. Thank you for being here, and the floor is yours.
Thank you. Well, thanks for turning up so early on a Monday morning. I'm notorious for speaking too quickly for my English language students. So if I'm going too quickly, put up a hand like this, you know, slow down, okay? Because I will slow down. But I want to, I think I've tailored this particular lecture will work in 2 hours. Tomorrow's lecture may be a bit of a problem, but we'll see how we go. Now, are we rolling here? Let's see. Okay. So I'm calling this a crash course in non-equilibrium economics because if one concept dominates how economists think about the economy, it's the word equilibrium. So I wanted to say, okay, let's look at another approach to economics which doesn't involve equilibrium. And I want to start by asking you whether you recognise or whether you can work out who said the statement I'm going to show you on screen right now. There's somebody saying we must distinguish between the statics and the dynamics of this discipline, subject. The real condition of industry is one of perpetual motion and change. Commodities are being manufactured and exchanged and consumed, and if we wish to have a complete solution in all its natural complexity, look at that word, natural complexity, we should have to treat it as a problem of dynamics. Now, who do you think said that and when? Any ideas? Pretty strong statement in favour of dynamics, isn't it? It mentions the word complexity. Pretty modern word. Any ideas at all? This one. The main concern for economics is that human beings are impelled, for good or evil, to change and progress. We use static hypotheses just as a fragment before we move on to the dynamics. But the central ideas must be of living force and movement. Any idea of who said that? Okay. First guy was William Stanley Jevons, back in the 1870s. One of the founding fathers of neoclassical economics. The second is Alfred Marshall. So if you go back to the founding fathers of this discipline, they are uttering words which would have modern neoclassical economists saying, you're a bunch of fools. Statics is all we need. Equilibrium. If you can't do an equilibrium, you can't do it at all. What on earth went wrong? My feeling is that if you look back at when these people were developing what became conventional economics today, they were looking at the neighbouring disciplines. They literally envied physics. They literally envied what was happening in mathematics. They wanted to bring those ideas across. Even though I think they did that very, very badly, they were aware of those ideas. Now, what happened is they decided they had to start with statics. That was the easier thing to do, and I think I've got that on the next page. Let's see. Of course, it was entirely in statics, and Jevon continued to explain why. He said, well, yes, dynamics is the right way to go, but it would surely be absurd to attempt to do this more difficult task when the easy one is within our grasp. We can do statics. Now, what then happened from that point on is the entire mechanics of the discipline stuck with thinking in equilibrium terms. And they became more and more isolated from other disciplines. And now I think their isolation is just ridiculously large. When you get physics listening to economists these days, they are normally stunned by how little economists know about physics, about dynamics in particular. So there was an isolation that began from that in an early decision, and we've continued down this isolated path. Now, Marshall was the same. Marshall said that, yes, dynamics and evolution are essential, but we're going to adopt statics as a stopgap measure, and we're going to leave it to our successors to do the dynamics. That was the idea they had. And here is him saying how important dynamics is, and not only dynamics but evolution. He said economic statics and dynamics are imported from physics. That's a very distinct statement. We borrowed this idea, these concepts from physics. Okay? Often economists will scoff at the idea that they began their discipline by borrowing ideas from physics. But here's Alfred Marshall saying quite literally, that's where I borrowed it from. Okay? Now, if you're actually getting the person who did the borrowing, one of the people, saying, yes, I borrowed from physics. He said, and discussions imply that they are distinct branches. He said, but of course that's not the case. He said, a modern mathematician, he's talking about somebody between 1880 and 1920. Okay, a bit old-fashioned from our modern terms, but that was modern, of course, in his perspective. The modern notion of dynamics includes statics. In other words, statics is a subset of dynamic analysis, not the other way around. Okay? And that's a big difference into how conventional economists think. So if a mathematician can solve a problem dynamically, he seldom cares to solve it statically at the same time. And he said all you have to do to get the static solution is set the rates of change of variables to zero, and then study what happens when they're at rest. So again, the starting point here is to say we are modelling something which is moving through time. So our economics is about things which are changing over time. And if we're going to do static analysis, then we say, let's set all those rates of change to zero and see what happens. It's not a case of saying we're in equilibrium now, we're going to move to a new equilibrium, and we can ignore time, which is fairly much what conventional economics does today. But he said, well, the static has also got some advantages. These are important advantages, according to Marshall. It's simpler. Now, of course, two intersecting lines, a lot simpler, I will agree, than a pair of differential equations. That's true. At least a pair of simple intersecting lines is simpler. When you try to model an entire economy in equilibrium, maybe that's harder than differential equations. He said it's useful preparation. So what you learn in doing statics will prepare you for doing dynamics. And finally, he said it might be the first step towards a partial solution when the complete complex one is just too difficult for us to do. So there's an awareness at the beginning of neoclassical economics that we should be doing dynamics. And that carries on over time because when asked in 1898 or 1897, depending on how long it took the journal to publish the paper, when asked what he thought the 20th century economics would be noted for, this particular author said, I expect it to be the century in which we change from statics to dynamics. He's talking, notice the strange thing about the 19th century. At the end of the 19th century, I believe there was some famous patent office person who said it was no point keeping the patent office open because everything that could be invented had been invented. Okay. At the end of that period as well, the physicists will realise there was something wrong, but didn't realise the dramatic changes that were going to come their way in the 20th century. Now here, at the end of the 19th century, most economists, according to this person, believe that the economics is also settled. Nothing new to add. This person is saying no. That's not the case. He said, most of my colleagues believe that we're pretty soon going to have a complete statement of all the principles of economics. We won't need to do anything more than just elaborate and teach. He said, I take issue with that. He said, the great development in economic theory is to come through the statement and the solution of dynamic problems. And that was J.B. Clark, pardon me, the person who developed the Marshall productivity theory of income distribution that neoclassical economics still uses today in varied ways, but it's still a central concept of that theory. Now, of course, that isn't what happened. That was 1898. So certainly it wasn't the case that the next century was, if you look back at the 20th century, the economics, you said, what would be the distinguishing feature of developments in the 20th century? You wouldn't say developing economic dynamics. Well, maybe you would. Because modern macroeconomics talks about being dynamic. That's the right word. Stochastic. And everything is subject to exogenous shocks. General. Equilibrium. Modelling. So isn't that dynamic? And I'm sure if I had a group of fairly strident neoclassical economists in the room, they would have been saying that to me already. Well, that's dynamic is good. Okay, we need to be dynamic. Stochastic is good because, as I've said, most things are subject to exogenous shock, so you need to include that inside there. General is also good, though I might, of course, I'll come back and question just how general that is. But equilibrium, how does that fit together? Okay. Conventional economists see no problem in that. And I think this is because they have a strong prior belief that the economy has to be in equilibrium. And I see this as coming from confusing an identity, which is a vital concept in getting the model correct, with equilibrium. Now, this strong prior was on show after the financial crisis in front of the Congress of the United States of America, because the American Congress organised a hearing, of all things, into economic theory. And they invited 5 people along. This is one of those 5 persons. And he's now talking about dynamic, stochastic, general, equilibrium, macro models. He said they have common features. They make sure they're consistent with national income and production accounts. Things must add up. Well, that's a good thing. Okay. They lay out how people make decisions. Now, I might interject inside there. They lay out how economists assume people make decisions. Not the same thing. Okay. But he's saying they continue how decisions are made. They're explicit about the constraints imposed by nature, so your resources constrain what you can do, the structure of markets, maybe. Available information. So it's a very, very big tent, he's saying. It's a very large, it's not a narrow area at all. He said, and also from this perspective, there is no other game in town. And he summarises this statement. A useful aphorism in macroeconomics is, if you have an interesting and coherent story to tell, you can tell it in a DSGE model. If you cannot, your story is incoherent. Okay? That's an extremely strong set of statements that what they're doing now is the only way one can do economics. And that's why the sort of work that I do is rejected out of hand by most economists. This was V.B. Chari, who's quite a significant macroeconomist, quite a bit of influence in the profession, and he's also, I do believe, a member of one of the Federal Reserve governing bodies. So, part of that statement, of course, because equilibrium is one of the words in there, what you're saying is an economic story must have equilibrium to be coherent. That's essentially what's being asserted there. Not at all. Because what's going on here, I believe, is a confusion of an identity which must be true at all times with an equilibrium which is only true when particular conditions apply. Now, let's look at microeconomics, the famous supply and demand curves. You have, for example, an identity that must apply there is that if you are measuring a model in terms of the quantity that is demanded by consumers and measuring what is sold separately, measuring what is sold by suppliers, you must have exactly the same number. Whatever state the market is in, the number of goods bought by consumers must be identically equal to the numbers sold by producers. Okay? That's an identity. In that case, I'm using the mathematical symbol for identity, the triple equal sign, rather than the double. They must be equal to each other. Now, if you had a model that had the amount being supplied differing from the amount consumed, your model would be wrong, would be incoherent. And that's the point that Chari was making. But does that mean that being not in equilibrium is being not coherent? Well, let's look at supply and demand curves. We have our little price and quantity argument. There's demand and there's supply. And then we draw in the equilibrium price and equilibrium quantity. Now, the implication here is that that's the only point that's coherent. But what about if you're in a disequilibrium situation, where the flow of demand, now I'm trying to put time inside here. Now think about supply and demand curves. You've never actually seen time included on those, have you? So what are they? Each of those curves allegedly states, you say the demand curve, states the quantity that consumers would demand given a particular price at some point in time. And the same thing for the supply curve. So I think what they're telling you, if you want to put them in a dynamic sense, if you actually want to interpret these as dynamic concepts, what you've got is one is saying, here's the flow of supply over time that will apply given a particular price. So each of those points on a curve is an alleged flow of supply per unit of time for the supply curve, flow of demand per unit of time for the demand curve. Those are what they mean. So if you're not where the two curves cross, then you're a point where the flow of demand differs from the flow of supply. Okay? So I can say, if I put it in dynamic terms, let's say we're at a point where the flow of supply is greater than the flow of demand. Let's say up here, the disequilibrium point. If I measure across there, that's the quantity that's going to be demanded, and that's the quantity that firms are going to want to supply. Now, which one is going to rule? What's actually going to be demanded and supplied? Where will the identity be on that diagram? Any idea? It'll be on the demand curve. That's the amount people will actually buy, and therefore that's the amount that sellers will sell. So you're going to be on the demand curve. So the quantity demanded is going to be the amount that's actually purchased. But the suppliers have got a bigger flow of supply. What's going to happen? Pardon? Yeah.
As far as I understand, it's not a problem that, the problem is not whether it exists theoretically an equilibrium, but rather if we will reach this equilibrium.
That's another important point, but I want to get this identity point out of the way as well. It's quite true. Once I've shown you can be anywhere on that diagram, then the question is, will you reach equilibrium over time? And then the other way you could put it to say as well, if you will necessarily reach equilibrium over time, then why bother with dynamics? That's another approach, okay? But I'm going to show first of all that it's the statement that Chari made about your dynamic stochastic general model must also be equilibrium, otherwise it's incoherent. I want to show that that's factually wrong. Because what's going to happen in this situation where the flow of supply is greater than the flow of demand is there'll be a change in the stocks that firms have got in their warehouses. Okay? Simple and obvious, isn't it, when you think about it? So the identity that will apply, this is a dynamic translation of that identity of supply is equal to demand up above. The gap between the flow of supply and the flow of demand will be identical to the change in stocks. And what's going to go on in this particular case is that many goods are going to be accumulated across that kind of time in the warehouses. And what you therefore expect is the factory would then say, the boss of the factory would say, slow down the production lines, producing too much, slow it down, stop pouring stuff. We've got stuff not going out of the warehouse. The factory's pouring stuff in from the production line. Slow the production line down. Okay? So that's your dynamic story. So the supply would adjust, and therefore the price would as well. Yeah.
You also have unsatisfied demand.
Pardon?
You also have unsatisfied demand.
Yes.
In some cases.
Well, that's
the other.
And that would be down the bottom. So I'd have it down here instead. And what I'd have therefore is these would be the amount demanded. That's the amount produced. The stocks would run down. Now it's a possibility they wouldn't have that many stocks. Okay? You can have a short side. So you then have another problem you'd have to bring inside there. Back orders. So I'd need to generalise that equation and say the change in supply minus demand would be identical to change in stock plus change in back orders, for example. Okay? So all those you need to generalise the simple equation I'll put down there. But that's to say in general that what rules is disequilibrium, not equilibrium. The focus upon equilibrium is an intellectual error from a starting point in the 19th century which acknowledged that dynamics was the right place to get to. And probably the best realisation of this made by any equilibrium-oriented economist was made by Irving Fisher back in the 1930s. Now, I really recommend reading some of Fisher's work. He's not a great writer. He doesn't write anywhere near as well as Keynes. And he has a complete epiphany at one point in his life. And what I want you to see is how profoundly and how well he responded to the epiphany. So beforehand he wrote fairly boringly about equilibrium finance theory. And after the crisis he wrote much more passionately, but still not as well as Keynes, about disequilibrium. Of course, the epiphany he suffered was being effectively made bankrupt and having his reputation destroyed as well during the stock market crash of the 1929 stock market crash. So here he is saying, what did I get wrong? Where did my previous beliefs lead me wrong? Because he was the person who developed the precursor to modern finance theory. He was the Sharp of his day in that sense. He was the person who developed the theory of finance markets. And he said, well, we might, and back to your point again earlier, we might well assume that most variables tend towards equilibrium, a stable equilibrium. He said, so unless any force outside the system intervenes, these oscillations will diminish and will head ultimately towards that equilibrium point. He said, but the exact equilibrium sought is seldom reached and never long maintained. So new disturbances are bound to occur. Come back to that stochastic point. If you got to equilibrium, a shock would come in, you'd be out of it again. You see? So the odds that you're going to be in equilibrium are vanishingly small. He said, any variable is almost always going to be above or below its ideal equilibrium. He said, theoretically, therefore, there must be over or under production, over or under consumption, over or under spending, over or under everything else. It is as absurd to maintain, assume for a long time, that the variables in the economic organisation, or any part of them, will stay put in perfect equilibrium, as it is to assume that the Atlantic Ocean can never be without a wave. So a fairly profound statement from a theoretical point of view, practical theoretical point of view, that we must be working in disequilibrium. If we're not working in disequilibrium, we're not describing the economy. So I'd go back to Chari's point, and I'd say for that reason the entire field of dynamic, stochastic, general equilibrium models are incoherent, because they assume either instantaneous movement towards equilibrium, in the case of what is known as the freshwater school, the new classical approach, or delayed because of frictions, convergence to equilibrium, when you're working in the new Keynesian approach. They're both incoherent. They're leaving out the fact we're always going to be in disequilibrium. And it rules real sciences as well. Now, I have a multitude of quotes on this front that I'm solely putting into a book I'm writing on this topic and others. Great, thanks very much. But here's just one that I found only recently from a physicist that I quite enjoyed. But this is actually preceding it, pardon me. What I've got here is a quote from a leading economist. And this is a paper written in 1999. And what he's doing in his paper is appealing to physics, to say economics is the physics of the social sciences. He's saying effectively it is the only true social science. He's saying, as in the physical sciences, equilibrium is a central concept in economics. Now, we go back and remember those quotes from Marshall and Jevons. They are aware that dynamics, not equilibrium, was the defining feature of the physical sciences in the 19th century. So what knowledge does this person actually have of physics to make a statement like this? He said, equilibrium is an essential concept. But now, and what he is saying here, and quite definitively and quite correctly, that virtually all economic theories has as a primary desiderata that the behaviour described must be consistent with some notion of equilibrium, not identity. Again, this confusion, equilibrium. He said, social sciences discuss, spillover effects and feedbacks, But amongst social scientists, only economists insist on a physics-style equilibrium as part of their analysis. Now, this person is actually quite a nice guy. I met him at a conference in Adelaide some years ago, and he was very honest about his experiences as Bush's chief economic advisor. Now, this was a working paper written before he became the advisor, and I don't think it actually got published. It's called Economic Imperialism. You can search for it on the web. And if I don't know it actually got published as a paper. I haven't been able to find a paper version. Probably I will if I take a closer look at the literature. But here he is insisting that economics should take over all the other social sciences, and a major reason why is it's like physics because it uses equilibrium. Well, that might have been vaguely true 50 years ago. But this is a physicist talking about modern economics, and he said the crucial thing for economists to do is to get past the archaic fixation on equilibrium and adopt concepts of non-equilibrium systems from the physical sciences, with giving the example of the Earth's atmosphere and the ecosystem. So the understanding they have of physics is incredibly primitive. In effect, they're projecting their technology onto physics, when physics uses anything but this technology. I have far more scathing quotes than this particular one, but I thought that was a nice little summary for this lecture. He finished up by saying economists are like weather forecasters who do not understand storms. They wouldn't do all that well, would they? Well, let's take a look at meteorology, because intriguingly this is an area which, like economics, used to practice an equilibrium-oriented approach to its discipline back in the 1940s and 50s and 60s. But in 1963, there was a big change, because after using all this linear equilibrium stuff and linear regressions and trying to look for patterns, this pattern looks like what it was 5 years ago, therefore we predict tomorrow's weather is going to be like what it was 5 years ago plus one. That sort of thing was being done. Yeah.
I think there were already like if you will, the d by dt in the equations was already there.
Oh yeah, I know. But
they were not only working on analogy or statistics.
I'd never accuse the meteorologists of being as bad as economists. Okay, I'm saying in general there was a tendency to use those technologies. They were part of the toolkit. Okay, I'm not saying they were dominant. And the important thing I'm going to illustrate here is how rapidly that particular part of the toolkit was thrown away when it was shown to be inappropriate. So, to quite a degree, that was a caricature of meteorology. I wish I was doing a caricature of economics. Okay? We should just chat over coffee shortly. Okay, but Edward Lorenz was a mathematician and a meteorologist, and he said, well, we all know, and this is again to come to your point as well, meteorologists were quite aware that nonlinear and disequilibrium phenomena were fundamental to storms. Yeah.
I also think that we are criticizing the definition of equilibrium in a very simple way. Because the definition of equilibrium that we saw in the first, let me say, PowerPoint,
Yeah.
it was very tough. It was not so simply as that. We have a theory of justice behind that Bauer has developed.
Theory of, pardon, my hearing is bad.
Theory of justice behind that.
Yeah.
Bauer has developed. And you don't have the equilibrium in that simple way, but you have many things behind. You have the price taper and all that. So you find it real equilibrium. It's not that easy that you don't have it. And there was a lot of discussion about that, and the models of general equilibrium are based on Bauer's theory of justice.
I actually I don't believe modern neoclassical theory is the use of Olra at all, because you no longer have multiple commodity input-output dynamics being covered. When they talk about general equilibrium models today, they're starting from the idea of equilibrium between the present and the future. Okay, they're not talking about equilibrium in multi-commodity input-output systems. When those models are used by treasuries and central banks, they may well then modify them to have multiple sectors and so on. But it's not what Volra had in mind at all. Volra was talking about reaching an equilibrium by trading many commodities with many buyers and many sellers to reach a single vector of price at that time. That's been abandoned largely because of a problem in the stability, which is your point earlier, stability of equilibrium. Because there's a series of papers coming across from mathematics that have proven that equilibrium is unstable. So we'll talk about that later. I did call this a crash course, by the way. I'm only giving 5 lectures, so I have to do some, cartoon version. When I come back for a longer period, we might spend a whole week on topics like that. But now back to the. And please, actually, I'm enjoying interjecting. Throw in, please, at all times. But I'm glad you're stopping me talking incessantly. But Lorenz said, look, most weather phenomena are nonlinear and disequilibrium. So to demonstrate that, he built a very simple model of convection. Now, if you ever watched a hot plate, you have a saucer or a pot on a stove, and if you watch it very carefully, you've seen that it's got these rotating cells of water. You see like patterns form on the surface, not when you're boiling it vigorously, but when there's the plate's on, the water's rising, and what you'll get is the water rises in convection cells. So he built a very simple model of that. And these are the equations for it. Notice they're all with respect to time. dx, dy, and dz. And it's an extremely simple set of equations. It is 3 differential equations, but they're actually incredibly simple. Because there's only 3 variables, x and y, which largely are there's several ways to describe them, but they can involve, if you imagine on that pot, whether the water's going left or right. Okay? And z, the temperature gradient. And 3 constants, sigma, rho, and beta. Normally I use A, B, and C here, but I'm using the terms that are used in the Wikipedia explanation of Lorenz here. And notice that all that's going on mathematically is either subtraction or multiplication. Those are the only 2 mathematical operations. No division, no raising to a power, no logs. Very, very simple set of equations. You wouldn't expect much to come out of that. Now, does anybody have their laptop and have Minsky, the computer software, with them? Do you do? Beauty. Anybody else? A few others. So you've got to load Minsky now. And what I'll do is we'll see how you go at building a model. I'll show you a movie of building the model built in here to show you how to go about building a dynamic model in Minsky. Now, Minsky is one of many programs that are called system dynamics programs. Just a few of them I've listed here. Simulink, which is probably the dominant one. Who came to Trond Andresen's course last week? A few. I know I've recognised a few faces. Well, Trond uses Simulink, and almost all engineers use Simulink. I think Simulink, as part of MATLAB, retails for about $20,000 per copy. Not cheap software. VenSim, most people working in social sciences use VenSim or Stellar. And XCOS is a free open source version. Now, Minsky has disadvantages compared to those programs because it's a very new piece of software. The amount of time that's been spent writing the code that actually runs when you run the program is about 1 year's worth of programming time by one person, about 2,000 hours of work. So it's very, very new. But first of all, it's free, and only XCOS is also free. But most importantly, and I'll be getting onto this more in my final lecture, it's designed to model monetary flows. And I believe as economists, we have to model the economy in a monetary way. I'll justify that in the 4th and 5th lectures. And Minsky is the only program that makes that quite straightforward. Because the disadvantage being very new, some bugs, we've knocked off most of the bugs of the version you're using right now. I found a couple more last night. I won't tell you about them. But you're not likely to spot them. But we're going to develop it much, much further, and hopefully with the help of Ecuador as well. So what is a program like Minsky? And this generally applies to any systems engineering program. First of all, it's a graphical user interface, or GUI. Is there a Spanish equivalent to the word GUI? Graphical user interface. If you hear a programmer talking about, I'm designing a GUI now, what they mean is the visual way that the user will interact with the software program. And what it does, it uses flowcharts to define equations. So here's a little movie, and this one certainly we can do real time in class. That's Minsky's user interface. So I'll bring up the actual program itself here as well. So as you can see, I've got a movie of that down here, and I'll quickly use this movie to build a model of f is equal to the sine of t. I'm slowing it down a bit here. And there's your classic sine wave. Now, I'll actually just do that in Minsky itself now. And I'll make it a bit, I might just, if I can stop, good, I can stop that, okay. This first item here is time. You don't normally need to use time in Minsky directly because it assumes time for most of its differential equations. But I'll bring t down here, and now I'm going to make the palette a bit larger so you can see it. And I'm going to I'll move that back up here a bit. So there's t. And I want to put it through, say, I'll put it through cosine here. There's cosine. And I'm going to create a variable. And I can use a name like y of t. Okay. And then if I drag a wire from the point of t to the cos and from the point of t to the y, I've now said y t is equal to cosine of t. The y of t there is just for, that's a label, not actually using t inside there, just to make it obvious if you produce a set of equations. Now let's graph it, bring down a graph, and then I go back to wire mode. At the moment you've got to switch between wiring and moving. Drag the wire, attach it there. Now notice I used this thing called Runge Cutter a while ago. That's because we're numerically simulating an equation here, and the steps we take depend upon parameters we feed into an estimation program, and at the moment the parameter is too big, it's 0.1. I'm going to make it 0.01. And now if I simulate this, I get a cosine function. And I can also output the equations. Has anybody here heard of what's called latex? No, don't. Yeah, okay. Okay. There's two versions of the word latex. I mean the mathematical one. So latex, if I output the latex here, and I'll just call this cos. Then if I go across to, let's go down here. If I go across to where I've got these files stored, there's cos.tex, and I have a latex program installed on my computer which will read this and translate it for me into mathematical equations. I'll make it a bit larger. And that's what I'm saying. So yeah, what you're actually doing is defining equations, but you're doing it using a flowchart rather than writing the equations out. But you can go from the flowchart to the equations, and in future development we intend being able to go from equations to the flowchart as well. Go both directions. At the moment we only go one. So that's Minsky, very simple way of using it. But of course, hang on a sec. Okay. What we really want to do is build dynamic equations. That was dynamic, sine was changing through time. But what I want to look is rates of change of variables. That's the essential thing to do in this sort of modelling. And there's one little trick that applies to all these programs, and that involves the numerical accuracy of a differentiation process versus integration. Now, integration is adding up, adding little steps. So if you already have a large value for a function, and you add another large value, the function's going to move a small amount. But in differentiation, if you're looking at the shape of a hill, and you have a sudden change in the slope, then the differential will be a large change. So for numerical accuracy, all these programs convert differential equations into integral equations. So what you have here is, rather than saying dx dt is equal to y minus x multiplied by sigma, these equations rework it to say x is equal to the integral of y minus x multiplied by sigma. Now what I want to show you here is a movie of how to build that system. And you'll see at the top of Minsky there's a palette, and in the palette there's a little block there with an integral sign and dt. So that's what you use when you want to define an integral equation directly. And this is defining the xt equation in Minsky. I hope you can see that. That's how visible that is. Okay, that's the window. Let's go. So you bring down an integral block. You can double click to edit it, change the name to x, give it an initial value of 0. Go up and bring down y. You can also right click, you get a drop down menu and choose edit, make that y. Initial value of 0 for that. Now I want to copy the y itself rather than the entire integral block. So I copy variable or copy var, and I do the same for x as well. Now I need a minus sign, so I bring down a minus block. And I need a constant. If I type a backslash key and put in the word, that this row here, it's sigma. Backslash of the word sigma will give you the Greek letter sigma when you put it on the palette. There's sigma. There's a multiply block. And I then click on the wire mode to wire them together. We'll make this, go to what they call mode independent wiring at some point. We haven't quite got there yet. So that's for defining the x equation in Lorenz's model. Look difficult? Not too bad, is it? Okay, pretty straightforward. We're borrowing ideas from all the other programs, but we're adding our own. So one thing that Minsky does is attach that integral block to a variable. No other program does that. Various little things like that. And we also have tricks about the multiply and minus. So if you want to multiply 15 things together, you can wire 15 things to one multiply block. Little shorthands like that. But that's what's happening. Now, has anybody done that in themselves in Minsky there? Have you done it yourself? Okay. If we had a lot of time, we were doing a seminar and we had large computers, I'd get you all to do this right now. But let's just see what happens if you do that and use the following values for the constants. So sigma I'm going to make it equal to 5, rho equal to 15, and beta equal to 1. Having done all that, what you get will be this. I'll just do it quickly here. So the same thing again, I'm going to go all the way through here. So there's x. There's y. And z. And the three constants. Sigma with a value of 5, rho with a value of, what was that, 15, and beta with a value of 1. And now right click and choosing copy variable, dragging it up there. Right click and choose copy variable for the x. Bring down a minus block. Bring down a multiply block. Wire that together. That's x defined. I need z in the definition for y. Rho minus z. A multiply block and the value of x. And minus y, isn't it? Let's see. wire that up. Okay. Bit messy. You spend a lot of time tidying things up with these interfaces. And now rows Z's a bit simpler, I think. Y minus x, or y multiplied by x, pardon me. And minus beta times z. Minus log. Now I want to bring down a graph. Two graphs, in fact. And they've got 4 inputs. Notice 4 inputs on the x, on the y1 and y2 axis, and 8 on the bottom. That's how you can combine together an x against a y. If you don't actually combine something against another variable, it just gets plotted against time. Now I'm making this range 0.01 to get that smooth plot and play. Isn't that exciting? That's equilibrium. What a fascinating weather system we have here. Okay. Well, of course I want to go beyond that. That's an equilibrium. Let's take a look at it. That's it there. So I run it, and I can run it for as long as I like, and nothing will ever happen. Okay. X and Y don't vary against each other, and Z just varies against time. Nothing ever happens. That's equilibrium in the weather system. Wildly exciting, and of course you can use it to forecast tomorrow's weather. It's going to be the same as today's. Nothing's going to happen. Let's just stop that and go back to the presentation. What if you have an exogenous shock? I'm going to add a little element here. Just grouping and moving that block up so I make a bit of space. I'm grouping it so I can see what's inside there again. Doing the same with this one. These are things we intend improving over time. We don't have a good copy and paste as yet, but we'll get there. So I'm just using this lasso to grab a group and then move it. And you can bend lines as well, as you can see there. Now what I'm going to do, okay, same as Z, okay. This is all in real time, by the way, so you can see fairly how quickly you can design a system. It'll take a lot longer to design one of the economy, I might add. I'm showing up a few of the commands here. But what I'm really aiming to do here in a moment is to add an exogenous shock. I'm adding a title to the graph as well. Making Z bigger so you can see what's going to happen here. Now I'm going to bring in a constant which I'm going to call shock. Give it a tiny value. And I'm going to make my x equation equal to the differential equation plus that shock. But I'm also making shock into a slider. This is a little trick where I can give a value for it and a maximum and minimum. So it's going to a maximum value of 0.1, a minimum of 0, and a step side of 0.1 because it can only be 0 or 0.1. And I bring down a plus key here, delete that line, right click and choose delete, then wire the shock in. So now I can give a shock to the system when it's in equilibrium. I'm saving it here before anything goes wrong. Now I hit run, nothing happens. Now I hit shock. Oh dear. Disequilibrium is rather different to equilibrium, isn't it? Okay. So that's the essence of what meteorologists learned 50 years ago, 1963. And what I'm trying to do with economics is say it's about time we caught up to the meteorologists. Let's take a break there. have a coffee break, and we'll come back in about 10 minutes' time.